Okay, so it's a great pleasure to have Noppadol Mekareeya. He's going to tell us about 3D mirror of the circle reduction on twisted theory of classes.
Okay, thank you very much. So first of all, thanks Satoshi for the very kind invitation. So in this talk, I will talk about a reduction of a class of 4D theories, okay, on a circle to 3D, and we'll talk about some mirror symmetry. So this is a work in collaboration with 3 people. First, Emanuele Berato, this is my PhD student from Bicocca. Simone Giacomelli is a postdoc in Oxford. And Matteo Sacchi is also a student in Bicocca. Most of you probably have known him from last week's talk, right? So, yes.
Yes.
So, let's me introduce the topic. So, yes. So, well, the main class of theory I'm talking about is a class S theories. These are a large family of 4D n equal to 2 superconformal field theories that may or may not admit Lagrangian description. Now, if you compactify this theory on a circle, they flow to 3D n equal to 4 theories. However, we can do a little bit more here. That suppose you take theory, you compactify, and you use a mirror symmetry. Usually, the mirror dual may admit Lagrangian description, and this is quite well known in some example by Benny Tachikawa and Shea back in 2010 as a so-called star-shaped quiver. So I will give some example of this. And mirror symmetry turned out to be a very powerful tool for this purpose. You can extract a lot of useful information of the 4D theory by the computation in the 3D mirror Lagrangian theory, because now you have mirror, and now you have Lagrangian. There is some computation one can do explicitly using the mirror description in 3D. Okay, so let me talk in general about this technique. So the Higgs branch is known to protect it against quantum correction. Also, when you reduce on the circle, the 4D Higgs branch is expected to coincide with the Higgs branch of the 3D reduced theory. The reason is that, first of all, we don't gain a hypermultiplet or anything like that upon reduction. And we believe that the Higgs branch is protected against quantum correction. So yeah, this is some expectation. I have no proof of this statement, but this is general expectation that one used. Now, if you use the mirror symmetry, the 4D Higgs branch become the Coulomb branch of the 3D mirror theory. So you can use, if 3D mirror theory has a Lagrangian description, you can use Lagrangian description to study 4D Higgs branch. Okay, so a consequence, some consequences of this expectation is that the quaternary dimension of the 4D theory, of the 4D Higgs branch theory, Higgs branch of the 4D theory, computer from 24 C minus A. C and A are the central charges, should coincide with the quaternary dimension of the Coulomb branch of the mirror. Global symmetry of the mirror theory should match with the Higgs branch of the global symmetry of the on the Higgs branch of the 4D theory. And if you have some quantity to compute, for example, Hilbert series, the Higgs branch of the 4D theory, this should be also equal to the Hilbert series of the Coulomb branch of the 3D mirror. Okay, but I should note that okay, so this, you can see that this is the relation between Higgs branch and Coulomb branch. Higgs branch is classically exact, but the Coulomb branch can receive quantum corrections. And symmetry on the Coulomb branch can get enhanced also from the description of the Lagrangian. And this is due to usually monopole operators. Okay, so this is an example of the type of theory that I mentioned. Let's suppose that you have a well-known TN theory. This is, you can get this from compactifying 6D 2,0 of type AN-1 on a sphere with 3 maximal punctures, let's say. So this is the picture of the 4D theory. Once you compactify on a circle to 3D, use mirror symmetry. This is turn out to be the Lagrangian description that I mentioned of the 3D mirror. And if you look at the dimension of the Higgs branch of the 4D theory, it's turned out to be this quantity. And if you look at the Coulomb branch of the mirror, and you compute the dimension, which is just the sum of the rank, taking care carefully of the an overall U1, then you get the same quantity on both sides. And in general, for a general N, the global symmetry of the 4D, the symmetry on the Higgs branch of the 4D theory is just SUNQ. This is global symmetry of the theory. And if you look at the symmetry of the mirror, it's also SUNQ. But SUNQ here, I have to emphasize that it gets enhanced from a bunch of U1s, topological symmetry, associated with each unitary group node. Basically, each UN node will give rise to one U1, which is topological, and these topological get enhanced. Okay. So even more, so for small number of n, the global symmetry can even get enhanced further. For example, as you know very well, for n equal to 3, this SU3 cube become E6. This is the famous E6 symmetry of the T3 theory. So, and let me also tells you that this star-shaped quiver, if you look at each of the leg, it's just 1, 2, up to n-1, and the central node here being n, you can take it to be un, but since there is an overall u1 that decouple, you can choose to decouple this an overall u1 from any node. Suppose you do it from the central node, then it should be called un mod u1. Okay, so right. So if you look at the building block, the partition 1, 1, 1, 1, 1, 1 n time coming from, you can think of it as in fact, it's a pairwise difference. Like you subtract n-1, you get 1, and so on. 2 minus 1 is 1, and 1 minus 0 is 1. Okay. So the building block of star-shaped quiver. So if you look at each leg of the star, it's come from TSUN theory. This is introduced by Gaiotto and Witten. And this is symmetry of the theory. It's a UN mod U1 times SUN. Okay. Now you can generalize this to any partition rho. Okay. And then the quiver still look like a star shape with the rank now being different from previous case. The building block of each leg is still this is a generalization of the 1, 1, 1, 1 of the 1 to n-1 up to n. It take a more general form n1, n2, nl, and n, such that these n are related to partition by again pairwise difference. If you take n, subtract nl, and so on, so the pairwise difference here will give you this partition. So the partition data can be translated into these ranks. Okay. And for each building block, you can see that these 3 legs coming from the partition data, row 1, row 2, and row 3. And the symmetry of these coming from this leg are coming from UN mod U1 as usual. This is from central node. And then for each leg, this is UR mod U1, where R is just the counting of the repetition of the number in each, in the partition of row, basically. So any question up to here? So to summarize, this is what I'm saying is that you have a class S theory of type AN-1. You reduce it on S1, you get some 3D theory, you mirror it, then you get some Lagrangian description. And indeed, this Lagrangian description contains some information about the original 4D theory. Okay. Now, the puncture, this is the type of AN-1. However, you can introduce something more sophisticated. It's called a twisted puncture, which means that since this puncture is a type from 60, you can regard it as some kind of a defect or this kind of thing. And you can use the monodromy around the puncture. You can use basically the outer automorphism of SUN to twist some of this puncture. So today in this talk, I will focus on the one type of twisting. Is that so you start with the classes theory of a type A even. Okay, A even is just SU2n plus 1, and there is outer automorphism that you can think of this as a Dynkin diagram, and you fold it basically. It turned out that once you do this type of the outer automorphism folding of this puncture, it's turned out to be that it's not just a partition of n anymore. Okay, this is not partition of 2n plus 1, but it turned out to be partition of 2n. This is called the partition of Cn. Is it has some feature once you do this. So you can do this to get something non-trivial. You do two. Suppose that you have a 3-puncture sphere. You do this type of automorphism twist on to 2 of them, for example. Then you get some new class of theory. So why this is interesting? Indeed, we know that in classes theory has been known since 2009. Okay, the twisted A2N theory was first proposed concretely only back in 2014, okay? And you might be surprised that actually many of their properties have been studied in depth quite recently. So let me review a little bit. So Kakatana, Disler, and Trim, back in 2014, they proposed a very nice superconformal field theory. It has a name R22N. So this is associated with a sphere with 3 puncture, where if you look at the puncture, this is a sphere of type 2n plus 1. So you look at this partition, it's a 2n, it's a partition of 2n plus 1. Obviously, this is called non-twisted puncture. But then the other two, you do this type of outer automorphism twist, then you go from a partition of 2n plus 1 to a partition of 2n, okay? So these two are called the twisted puncture, and we denote by T, just to label twist, okay? And okay, this is probably one of the only one actually that we know since 2014. Now, in 2018, it was shown by Tachikawa, Wang, and Safria that actually, if you look at the global symmetry associated with this, it carries a Witten anomaly. So this is quite a very interesting feature, and it's quite recent, as you can see. And even more, that Omori, Tachikawa, and Safria, back in 2018 again, that some of the twisted 2n theory can be even obtained from the 61,0 with a non-trivial Stiefel-Whitney class, okay? So this is quite interesting. Now, back to these years, I think, again, I mean, not many theory were known. Probably it's just a subclass of R22N and for various N. However, a few months ago, I would say that there are many more A2N theory that have been identified and studied. This is by Beam and Pelas in this year. So what do they show? I mean, it turned out that they show that the fixed point of these many of these twisted A2N theories. So basically, a sphere with 1 non-twisted puncture and 2 twisted puncture can capture even further superconformal field theory that we know. And it's quite surprising that you can do this. So what they propose is that you can describe a class of Argyris-Douglas theory, for example, and many other theory, which I will show, using twisted A2N theory. So Their fixed point involve Argyros-Douglas type theory, whose Coulomb branch operators are of half integers dimension. Okay, so they show that they can this type of theory belong to this class, which is quite surprising if you think about it, because we were taught as a law that the class S theory with regular puncture, including the twisted one, can only accommodate integer scaling dimension. But what is surprising is that for half integer dimension also belong to this class, and this is, to me, this is quite surprising. Okay, so what did they do, Beam and Pilas? So they're matching A and C central charges with the known Argyros-Douglas type theory that they propose. They can compute McDonald from the puncture structure. They can compute McDonald limit of the superconformal index. So basically, it's just it's part of the it's a limit of superconformal index. It's called McDonald index, basically. And they start the Higgs branch of this theory using a technique of the vertex operator algebra. Okay. Now, since from this work, the significance of this work is that instead of just having one type of theory, which is R22N that I mentioned here, now you have a large class of theory, which is quite interesting in each of them, and you can do many things with it. So in this work, what we are doing is that we propose the mirror, the Lagrangian description of the 3D mirror upon compactification of this theory on S1, basically. So let me, before going into more detail, let me talk about the classic R22N theory. So as you have seen from this slide, that R22N theory consists of one, this is called minimal non-twisted puncture, and then two maximal twisted puncture, okay? So let me start slowly review this. So the untwisted puncture, the minimal one, give rise to a U1 global symmetry. Usually when you have puncture, you have a global symmetry associated to it. And the twisted puncture, each of them give a USP2N global symmetry. So in this case, if you compose them together, you have a theory with U1 times USP2N square global symmetry. It turned out that this theory you can check by computing index or by Hilbert series or various quantity. It turned out that it has, yes.
Sorry to interrupt. Can I ask you?
Yes.
So these AD theories obtained by twisting, it is giving you half integer scaling dimensions.
Right.
Is there any hope for the other fractional dimensions?
No, I haven't seen it. I mean, we also tried, and I mean, as you know very well, this will capture something like A1D4 theory, as you will see. Yeah. For other dimension, I cannot see.
Is this has to do with the nature of Z2, or
it has something to do with Z2? Yes.
So
yes.
Yeah, because there can be Z3 twisting for a very special case.
Indeed. There was another type of a C3 twisting. You can try to play with those. Probably those will give something richer. This I don't know.
Okay, thank you.
So you mean that, for example, you can take a C3 twist of the SOA type, right? Or yeah. So, but in this case, let me, yeah. So it's encompass the half integer dimensions. Yeah. So you have U1 times USP2N square, which turn out to enhance to USP4N times U1, where this USP4N carries with an anomaly. Okay. So let's try to understand this theory a bit better. So you can do mass deformation for this U1 symmetry of the R22N. Okay. What you have is that if you do this mass deformation, you get SO2N gauge theory with 2N flavors of a fundamental hypermultiplet. This turned out to be an IR-free theory with the USP4N flavor symmetry. And the UV completion is turned out to be this conformal field theory R22N. The way to realize, for example, this infrared free theory is to realizing it from a brane construction where this is the construction where you have a half NS5, two half NS5, ND4 on top of orientifour plane. Okay, so this is the description. You can see immediately from here that this USP2N has Witten anomaly because there's a 2N plus 1 here, right? This is the odd number. So you can see that this USP2N has a Witten anomaly just looking at this diagram, okay? So now let's go back to brane perspective. That D4 brane on the O4 plus tilde realize a 5D USP2N theory at the theta angle equal to pi. And this theta angle is controlled by the group pi 4 of USP2N, which turn out to be Z2. This also control Witten anomaly, okay? So now the Witten anomaly, since this is upon the mass deformation, but by anomaly matching, this should be the Witten anomaly of the USP4N of R22N theory, which is the UV completion of this theory also, okay? And the UV completion, you can also see it nicely because this is IR-free theory. The UV completion arrives at infinite coupling. So what do you do when you want to go to infinite coupling? You put these two half NS5 on top of each other, okay? So when two half NS5 are on top of each other, which means the gauge coupling goes to infinity, yeah, so 1/2 NS5 plus 1/2 NS5 become full NS5. Then you get this full NS5, you can realize as the minimal untwisted puncture. And the two set of semi-infinite D3 on O4 plus tilde can be realized of the two maximal twisted puncture. And this realized the construction of the 2N, okay? So this is just to show the relation between okay, so you can see from this picture that you have Witten anomaly for the USP2N, and this relate to the O4 plus tilde construction. This is the type 2A realization, basically. And yeah, you can realize this simple theory using from the maximal twisted puncture from this part and this part, and minimal untwisted puncture from the 2NS5, 2/2 NS5 become full NS5, okay? Right. Now you could ask, okay, fine. Now we have the 4D theory. We have, we know the classic star shape quiver. So suppose that you compactify these theory into, on S1 to 3 dimension, what would be the look of it? So our claim is that the building block for the star-shaped quiver turned out to be, the crucial one turned out to be so-called USP prime 2N. USP prime 2N is turned out to be that you realize it from, it's really similar to what Guy Otto and Witten construct, of course, although this is not explicit in their paper. ND3 brane on top of O3 plus tilde between ending on a half D5 and half NS5. So this is the type of quiver. It's a quiver which has some feature that is alternating USPN and SON, okay? You could ask me a subtle question, why this is SO, not O, and this kind of thing, okay? This has to be justified later by computation, okay? But at the moment, I claim that it's SO, okay? And so if you have a maximal, the partition, one of the two to the 2N of this theory, it turned out to be this long chain alternating between SO3, USP2, SO5, USP4, and so on, okay? And for special one, for the this rho equal to 2N, it turned out to be this SO1 with the 2N, which means that this is a theory of 2N free half hypermultiplets, basically. So now you can form something like a star-shaped quiver, where when I put star shape in a quotation mark, because the following. So you take a 3 building block. Suppose you have untwisted puncture rho and 2 twisted puncture sigma and lambda, okay? You glue them together. However, you can see that the symmetry, something doesn't kind of match. Because on one side you have a SU2n plus 1, the other two you have USP2n symmetry. So what you need to do is that you gauge the common USP2n symmetry of these three theory, but then you have to decompose SU2n plus 1 into USP2n times U1 in the following way. So you take the quiver of this thing, you decompose SU2n plus 1 into USP2n, U1, and then the tail looked the same as before. This is given by the partition. And then you gauge common USP2n. So let me give you an explicit example. Suppose you have this type of puncture, okay? So these are building blocks that I just quote from the previous slide. What you need to do is that you glue together USP2, okay? This is the blue node here. SO1 is the pink node here, as the red node here. SO3 is the red node here. Then you have to decompose SU3 into USP2 and U1, and then attach it to U1, U2 as usual. Okay, so this is our proposal for the 3D mirror. Okay, now with this 3D mirror, you can compute a lot of quantity, of course, given it to be a superconformal index or something like that. Okay, the only difficulties is that the group has a mixture of unitary, symplectic, and special orthogonal. Okay, so okay, then but since we want to study only the moduli space of this theory, we use a much more kind of the limit of the index, if you want, in some cases. Okay, that to compute, so for example, you can study Coulomb branch of the 3D mirror theory, and you can match it with probably Higgs branch of the 4D parent theory. There are two ways of computing Coulomb branch of the mirror theory, namely the Hilbert series. It's come with two type of formula. One is called the monopole formula. This is highly sensitive to the quiver data that I told you. And you can refine certain fugacity and so on. So basically, these quantities are like the index in a lot of ways. You can refine the fugacity with respect to symmetry, but some of them are not so visible. I will give you some example. And this is you can see that this is accidental symmetry that emerge in the infrared, but you cannot see it from the ultraviolet description. You can also study the Higgs branch of the mirror theory, and even the Higgs branch of the mirror theory can have some non-trivial information about the 4D parent theory. So let me give you example. So first example is the two copies of the A1D4 theory. Okay, this is a Argyros-Douglas theory with SU3 symmetry. And so the claim is that if you give this puncture, this should describe this type of theory. So the building block is from 1 to the 3 is U1, U2, SU3. And then USP2 prime 2 is SO1, USP2. Okay, and then you attach it like this. Now, interestingly, this is an SO1, meaning that you just have a half hypermultiplet here. Since it's SO1, the gauge is trivial. So you can combine it into SO2, okay? Like in this picture. Now, okay, so let's look at some properties of A1D4 theory, okay? So the Higgs branch of the A1D4 theory is turned out to be the closure of the minimal nilpotent orbit of SU3. This is basically, if you want, this is centered one instanton moduli space of the SU3 group. And if you reduce this theory on S1, it turns out that you get a 3D n equal to 4 U1 gauge theory with 3 flavors. Again, the Higgs branch, you can see that it's the same here. It's a minimal nilpotent orbit of SU3, and the Coulomb branch turned out to be C2 mod Z3. Okay, so what is the expectation for this class S theory? You expect that the Higgs branch of the mirror is swapped, right, to be C2 mod Z3 square, because you have 2 copies. And the Coulomb branch turned out to be minimal nilpotent orbit square. Indeed, you can check by counting dimension as a simple exercise. The dimension of the 3D mirror, it just add up the rank together. Okay, so this is 1 plus 2 plus 1, and you get 4. And indeed, this dimension of the minimum nilpotent orbit of SU3 square. You can do Higgs mechanism and compute the Higgs branch of the 3D mirror. It turned out to be 2. Again, this is the quaternary Higgs branch dimension of the C2 mod C3 square. Okay, and this is the global symmetry that you should expect. Now you can compute it using this monopole formula. So you really use the quiver description. You feed it into some formula. It consists of some monopole operator dimension and a certain contribution from the scalar field in the vector multiplet. So let me not go into the detail of this formula. Of course, I'm happy to discuss what happened. Now, let me emphasize here the feature of this formula, that you have two fugacities that you can turn on according to this. Is the topological fugacity associated with this node and then with this node. So you see that even from the Hilbert series or index, the fugacity that you can turn on is this part and this part. And if you compute this summation, you obtain the Hilbert series of the minimal nilpotent orbit square of SU3, okay? However, there is some subtleties here. The symmetry of the, if you take a minimal nilpotent orbit square, you have the product of two space, it should be SU3 square. But here you can see that you can refine the fugacity from the Hilbert series or from the index. Only two fugacity, meaning that you only see the diagonal of SU3. But the whole space, you see that this is the space of a minimal nilpotent orbit square. So you see the whole space, but you can only see half of the symmetry of this space. This is quite a nice feature of this thing, that symmetry get double in the IR, but you from the UV, you can only see a diagonal subgroup of it. Okay. I hope this is clear. So basically, you can see that the diagonal SU3 coming from the enhancement of a U1 square here. Okay. But further, you should indeed have the full theory, should the Coulomb branch, the full Coulomb branch symmetry should be SU3 square. Why? One explanation is because of some monopole operator of this has something to do with that USP2 node is balanced. So USP2 has 4 flavor, and according to the rule that the symmetry get double in this case. Okay, so this is one nice feature that you can see, and indeed you can compute Higgs branch of this theory, and it turned out to be 2 copies of C2 mod C3. Higgs branch doesn't have, well, because it's a classical exact object, so you don't see the hidden symmetry in the, as in the case of Coulomb branch. Okay, so symmetry is straightforward. You see there is a Higgs branch symmetry is a U1 times SO2, so you can refine in this case, and indeed. Symmetry of C2 mod C3 is U1, C2 mod C3 is U1, so it's matched nicely. And indeed, from the Higgs branch computation, you can even nail it down that the gauge group that we propose should be SO1 rather than O1. Because if you have a O1, you have to gauge further this fugacity Y. You have to sum over it with a plus minus 1. Then you wouldn't get the answer that you expect. So we propose that the gauge symmetry here has to be SO1, and we propose that it should be SO for every theory. Okay, so this is example number 1. Any question at this point? Okay, if not, I will go ahead with the A1D4 with a free hypermultiplet. Okay, so now again, you composing using the same rule as before, and this is the proposed 3D mirror quiver. Now, what is the expectation? The expectation is that because A1D4 with a free hyper, you expect that the Coulomb branch of this theory should be C2 times the minimal unipotent orbit of a SU3, because this A1D4 and the free hyper give rise to C2, and the Coulomb branch of the mirror is C2 mod C3. And now you have a second description, in fact, that you know that the ADHM, this is the feature of the ADHM construction, basically, of the SU3 instanton, that this match with the Coulomb branch and Higgs branch of the U1 gauge theory with 3 flavor with a joint, in this case, it's just neutral, but this hypermultiplet. You know that this theory admit a mirror, which is look like triangle. This is affine A2 Dynkin diagram with the 1 flavor attached to it. Okay, so these two are mirror to each other. So now we can even propose a new duality. It's a duality, it's not just a mirror. That you have this theory dual to this theory. Dual means it's if you compute some quantity here, you compute some quantity here, it's the same. Higgs branch here match with the Higgs branch here. Coulomb branch here match with the Coulomb branch here. So what do you expect? What's a feature of this duality? Here you have 3 U1 gauge group with 1 flavor. Here you have U1, USP2, SO1, SO3, and then U1. So it's a highly non-trivial type of duality that between unitary quiver with all unitary gauge group and quiver with unitary mixed with special orthogonal and symplectic node. Okay. So again, you can compute a certain quantity to study this theory and match with the expectation from 4D, for example. The Coulomb branch, again, you can compute and you get indeed C2 times minimum unipotent orbit of SU3. So let me emphasize, this theory flows in the infrared to a decoupled hypermultiplet, a free hypermultiplet with something non-trivial, okay? So you can ask, first of all, where does the free hypermultiplet come from? Okay, so it turned out that free hypermultiplet coming from this part. This is the fugacity Y, which is not so visible in the Lagrangian, okay? Yeah, this part. And then the rest of the theory give rise to this minimum unipotent orbit of SU3. So basically, yeah, as I said, fugacity Y, this is basically this part give you the free hypermultiplet. And then the topological symmetry associated with this U1 combined with the SU2 of the symmetry of the free hypermultiplet and become Cartan of SU3. This is how you see the symmetry enhancement, okay? So it's quite a exotic one, okay? So now, okay, now you can also look at the Higgs branch Hilbert series, you get the C2 mod C3 as you expect, okay? So any question for these two examples? So of course, this mirror, you can match it with the 4D data. You can, as a byproduct, you also have new duality, quite interesting. And now, let me go to the last example, which is example number 3. And then I will discuss another powerful tool of having Lagrange. Okay, so now let's go back, let's go to the third example. This is called the C2U1 theory or R2,2 theory. This theory turned out to have a USP4 times U1. It's a rank 2, it's a rank 1 superconformal field theory with this global symmetry. Okay, this is the puncture. Again, I'm not going through the detail. The proposed mirror quiver can be done as before. Now you have these 2 copies of SO3 USP2. So you expect of having SU2 square symmetry, and SU2 square symmetry enhanced to USP4. And on top of this, you also have topological symmetry coming from here, and this gives rise to USP4 times U1, okay? You can compute dimension of the Coulomb branch and the Higgs branch. Okay, dimension of Coulomb branch of this quiver is 4. You add up the rank, and indeed it's matched with the Higgs branch of the 4D theory. Now, what is interesting is that Higgs branch of the mirror turned out to be 1/4 of the dimension. And you know very well that a hypercalar cone with one quaternionic dimension has to be orbifore of C2. So it's C2 of mod gamma. Would you like to guess what is the gamma is? So this theory has a very interesting feature. So since you have Lagrangian, you can perform this type of computation very exactly. What is interesting is I can show you actually, but upon computation, this turned out to be the Higgs branch of this theory turned out to be C2 mod Z6 actually. The number 6 is to me is quite non-trivial. Why? Okay, we will see. So yes, new result. The Higgs branch of the mirror quiver turned out to be C2 mod Z6, and the C2 mod Z6 turned out to have I don't have a rigorous argument for this, but you can construct C2U1 in another way from F theory. That you take a 1D3 brane probing a background, which is a combination of the 7 brane on type H2, and then you do a Z2S4 action. This is the technique that they use in this paper. So if you look at the singularity of type H2, you get a Archias-Douglas theory of a type A1D4, right? Whose Coulomb branch upon reduction is Z2 mod Z3. And once you combine the C2 mod Z3 with the S4 action, you get C2 mod Z6. This is quite interesting. First of all, you see that this is a one quaternion dimension, a hypercalar cone. You know immediately that it has to be C2 mod gamma, and the rest you have to figure out the physics of this gamma. And it's turned out to be Z6 because of the F theory construction. So indeed, this is connected to the construction of this theory in an exotic way, I would say. And the fact that it's one quaternionic dimension, it matched with the 4D theory being a rank 1, because you compactify the 4D theory with the one-dimensional complex Coulomb branch, you get a one quaternionic Coulomb branch dimension of the 3D theory. Okay, that's nice. Now you can even compute the Coulomb branch of the mirror. Then it's turned out to have a nice closed form, which match with another description actually that people came up with, known as a magnetic quiver. I'm not going into detail, but just to confirm to you that this is symmetry. You see the symmetry of C4U1 and disagree with the other computation. Okay. So I wonder if you have any question at this stage. So if not, let me go to the last part of the talk. And this is the power of having a Lagrangian description. So you could also study mass deformation of the 4D SCFT using a 3D mirror quiver. So let me explain to you why this is interesting. So suppose you have a 4D theory and you don't have really n equal to 2 Lagrangian description of this 4D theory. And you can ask, but you have a global symmetry. So you can turn on masses of those global symmetry and you ask, where does the theory flows to? Okay, so this is the main question. It's very difficult. Okay, you can do it in the level of the curve and so on, but it's highly complicated. Okay. Now, suppose that you have a 3D mirror quiver. You can translate all of this problem in another way, saying that, okay, you can turn on mass deformation in 4D SCFT. Now, it doesn't care whether it has Lagrangian description or not. But you have a Lagrangian in 3D mirror, so you can turn on appropriate complex Fourier-Illopolos parameter in the 3D mirror and study how the theory flows. So let me give you one example. This is quite a nice example of a C2U1. So C2U1, as you see, it's described by this puncture sphere. So it's a class S. You can deform this theory by turning on mass deformation. Where does it flow to? Okay. Let's answer this question using the 3D mirror. So this is the mirror description. Now you turn on a complex Fi deformation on this U1 node. Okay. Then upon turning on this, you use equation of motion. It will tell you that the wave you have to give the wave to the U1 gauge times U1 flavor. So the wave of this hypermultiplet. Once you give wave to this vacuum expectation value to this hypermultiplet, you break U1 gauge times U1 flavor to a diagonal U1. So you go from this theory to this theory. So you see, this kind of game is really explicit because you can use equation of motion, you can play with the vacuum expectation value, whereas in 4 dimension, you don't have any data like this because you don't have Lagrangian. Now you realize that with SO3 group connected with USP with one flavor charged under this USP2, you can translate it into a class S language, which turned out to be T2 gluing by USP2 in the middle. So these are the mirror game that you do in the theory. Now the right quiver is just the S1 reduction of the untwisted A1 theory on the genus 2 Riemann surface without puncture. Genus 2 because you have these 2 loops basically, and without puncture because you don't have an extra flavor. Okay. Now what do? You do mirror again because now you're in a mirror frame. You want to go to original frame. You mirror again. And you know very well that the untwisted A1 theory with genus 2 is translated into SO3 gauge theory with 2 adjoint hyper. Okay, this is a known result. Okay, since you have SO3 gauge theory with 2 adjoint, this is the mirror of this mirror description. So you go back to original description. You can give mass to one of the adjoint hyper. And then you get SO3 gauge theory with 1 adjoint. But this is so-called 3D n equal to 8 SO3 super young mills. So this is the 3D perspective. So what do you expect from 4D perspective? You expect 4D perspective that it's, you start from 4D n equal to 2, C2U1 SCFT. You give mass deformation. It can land on 4D n equal to 4 SO3 super young mills. Okay. In fact, this deformation, fortunately, has been studied by these people. And we agree with them, of course, using the mirror quiver. And I would like to also point out that by giving mass deformation, both in 4D or giving complex FI deformation in 3D, you get an RG flow, which has a supersymmetry enhancement. So you can see that the n equal to 2 supersymmetry get enhanced to n equal to 4 supersymmetry. Okay, and we can even identify the theory. Okay, this is very nice. So then we can say, okay, this is known result, fine. You give another way to support it, but what about new result? Yes. So there was also a new type of theory. This is a rank 1 theory, rank 2 theory with the symmetry SU3 times SU2 square. Okay, this was first proposed as by Beam and Pilas in that paper. It's called T3 Tilde theory. And this is also studied by these gentlemen with another name, okay? So the mirror quiver is this one. So with this theory, it's very hard to study. Okay, now it's not just a rank 1 theory, it's a rank 2 theory. So what do you do? Okay, you use this proposed mirror quiver and you try to do the same technique as before, okay? Now we have a new prediction. The prediction is that this theory can be mass deformed into 4D n equal to 4 SO4 super young mills. And again, Susie get enhanced in this deformation. So let's see the process. So again, the trick is to turn on the complex FI parameter for the U1 node, okay? You can do this in other node as well, but okay, take the simplest one. Okay, then this by equation of motion is amount to give a vacuum expectation value for this bifundamental. Then you break U1 times U2 to a U1 and reduce the quiver to be like that. Okay. Now, this you can use another equivalent description of class S, similar as before. Now you have extra U1 attached to it in comparison with the previous example. Doesn't matter, it's fine. You can study the mirror of this theory again. It turned out to be USP2 times USP2. Well, this mirror is known actually by Noppadol and Shear. It turned out to be USP2 times USP2 with 2 adjoint and then one bifundamental. And on top of that, this technique allows you to study the discrete quotient of this thing quite rigorously also. We see that there must be a C2 quotient of this USP2 times USP2. So you conclude that this is has to be SO4. You have this turn out to be equivalent to SO4 theory with one flavor and with a adjoint of SO4, okay? Now you can turn on a mask of this thing. Since you do the mirror of the mirror, so now you go back to the mask, okay? Now you can turn on the mask for this and then you land on 3D n equal to 8 SO4 super Yang-Mills. So one of the conclusions, and this is new prediction, is that the 4D n equal to 2 T3 Tilde theory can be mass deformed to the 4D n equal to 4 SO4 super Yang-Mills, okay? So this is quite a consequence of having Lagrangian in the 3D theory, that you can study mass deform of the 4D theory using Lagrangian in 3D. Okay, so let me conclude. So we propose a quiver description for the 3D mirror dual of a S1 reduction of the 4D n equal to twisted AN theory of class S. Many tests of the proposal, including a Hilbert series and a complex FI deformation. The 3D mirror is a mixture of a unitary, symplectic, and special orthogonal group. Okay, and the quiver are just gluing of this theory in the form of a modified star-shaped quiver. It's not quite a star shape because you have extra flavor attached to it. You can study many properties of the original 4D SCFT while the quiver of the 3D mirror, and study various mass deformations. Some of the latter has a SUSY enhanced RG flow. Okay, so let me stop here. Thank you.
Sorry. Thank you very much. Is there any question?
Hey, yeah, I have a question.
Yes, please.
Yeah, actually here, you mentioned that there are some RG flows from C2U1 to SO3
yes.
and 4. Yeah, here I have a question is, this for the 4 theory, we will have some one form symmetry. How about this C2U1 theory?
Oh, so you said there is, okay. One form symmetry in this theory, this I'm not sure. Given a class, theory of class S, maybe you can tell me, is there a way to read off one form symmetry?
I'm not sure how to do it.
That would be an interesting question. It's true that I agree with you that SO3 theory has this. But from the SCFT the C2U1, not immediate to me at all. This is a rank 1 theory. Maybe, okay, I have to take a look because this is in the class, in the, I don't know whether someone has studied this thing. Maybe some of the audience know. This I'm not sure that this is.
I don't know an answer to this particular question, but there's a paper by Yuji Tachikawa some time ago where he was able to translate just higher form symmetries in terms of class S data, I think. So if my memory is correct, that the basic building block theories, like 3 puncture sphere theories, didn't really have the higher form symmetry, but I might be wrong.
Yeah, I have no idea. Yeah, it seems the puncture is sort of subtle to deal with, right?
Right. So whenever you have, well, it's not always true, but for the simplest case would be like if you have a linear quiver, like then there is well, if it's a linear quiver, there isn't any one form symmetry because there is a fundamental hypermultiplier that breaks the center symmetry.
Right.
So you should get rid of the fundamentals. So that is possible when you have a loop in the quiver, because there's a diagonal Zn that does not act on anything. So then you have a center symmetry, center one form. But I guess for three puncture sphere, there isn't any, well, at least there is no analog of the center one form symmetry. But I might be wrong. There might be something.
Yes, so if this is true, then the one form symmetry in the Fourier-4 is really emergent, right?
Yeah, one could expect that. Even in this paper, they were really careful that they said they didn't specify the group structure of this thing. They specify gauge algebra, which is of SU2 type. Okay.
Yeah, I mean, if it's SU2, then I mean, SU2 or SO3 both have for one form symmetry. Just
yes, the reason that I specify SO3 here is because the mirror you have to mod U1. When you do mirror, it's turn out that the correct group that you have to do is U2 mod U1, which is turned out to be SU2 mod Z2, which is SO3. This is how we managed to pin it down that it is this one. Yeah, but I don't know. Yeah, it's an interesting question whether this one form symmetry is emergent or not, right?
So the related question maybe is that, can you like derive this mass deformation from the class S viewpoint?
Yeah, this in this paper, well, they didn't do it from the class S viewpoint actually. They for this specific theory, they did it from the I think from the singularity, right? Because it's a rank 1 theory. So this is they deform the singularity structure. This from my understanding. Now from the class S viewpoint, so if you not clear to us at all. I mean, we were thinking of course about this question. For example, if you take this theory, yeah, without knowing the mirror, and you give mass deformation, what is sometime if the theory is simple enough, maybe you can do, right? Because you know.
Yeah, I mean, for some simple cases, well, the mass deformation typically like triggers some kind of merger of punctures, so that like your regular singularity becomes irregular singularity. So typically you form a irregular puncture because, I mean, for conformal theory, if you turn on mass, then that will render the theory to be non-conformal, right?
Yeah. Like,
but this is a peculiar type of deformation.
So you can start, say, you can also ask, I didn't have it on my slides. For example, A1D4, you can, of course, mass deform it to, say, A1A2, right? So, sorry, yeah. So basically, or A1A3, I think you can do this type of game for that simple theory. But for when you have more complicated puncture like this one, to me it's not to me it's not clear at all.
Yeah, by the way, there is a non-Lagrangian way of implementing mass deformation. So
non-Lagrangian way of the implementing. Yeah. Can you maybe clarify?
Well, it's sort of technical, but the basic idea is that once you add a relevant operator into your effective Lagrangian, this is non-Lagrangian theory, but anyway, suppose you it triggers an RG flow to a conformal fixed point, and this added operator in the Lagrangian will eventually become R charge equals 2 in the case of Fourier, in the Fourier equals 1 sense. But that R charge has to be different from the R charge in the UV that you started with. So it has to mix with other flavors that this operator is breaking. So there's some mixing of the R charge, and then that you can fix that, which will eventually tell you the charge contents of that. And that will shift the value of the R charge, from which you can actually deduce the central charge of the IR theory using the anomalies of the UV theory.
Okay.
Once you know how the R symmetries mix in the IR, then you can actually use that to deduce A and C and other anomalies. So in that way, you do have an access to the IR fixed point.
So you have some access to A and C, right? Okay.
Well, at least if you know all the anomalies, then the anomalies in the IR theory can be also deduced in this way.
I see. Okay. Yeah.
You can play the same game with, if you know the index or like an index in the UV to the high precision, then you can also deduce the index using the same way.
This has to be full index, right? Or some limit.
Yeah. Like technically, this has to be full index. Otherwise, you cannot really perform this calculation because it involves mixing. And if you know a Shor or McDonald limit, this information is, you don't have enough information. You also need to have a fully refined index to do
right.
this.
Okay, so then if you have a 4D n equal to 1 Lagrangian of this, then you can perhaps check.
Well, if you have Lagrangian, then you already know what to do.
Yeah, for this one, I found it, because you can squeeze everything even here in one slide, right? I mean, it's a chain of duality. You can use in 3D.
But anyway, this is neat. Yeah, very nice.
Any other questions? Okay, if not, let's thank the Noppadol again.
Thank you so much.
I will switch off the recording and then leave the space for informal discussion.